Welcome. We are looking at some case studies. We have looked at least 4 cases. We have looked at spinodal decomposition, ordered domain growth structure, grain growth, and Gibbs-Thompson effect. And in this lecture, I want to treat a case where we have a situation where it is not sufficient to solve just the Korn-Hilliard equation or the Allen-Kohn equation. You have to solve the combined equation. So, you have to solve both Korn-Hilliard and Allen-Kohn. So, there are some physical scenarios where it is relevant, and there are some problems for which from a formulation point of view this becomes important. So, let us look at the physical scenario first, and then we will justify also from the formulation point of view why one might want to do that. So, let us consider a binary alloy. For example, let us say that I have a B alloy and I am looking at the microstructure. So, let me say that the matrix is A rich, okay. So, alpha is A rich matrix, and then let us say that I have some precipitates. In the precipitates there might be 2 different types, okay. So, this is beta 1 and this is beta 2. Both beta 1 and beta 2 are B rich, okay. So, these are the 2 precipitates. Let us say that beta 1 crystal structure is not the same as beta 2 crystal structure. So, if this happens, then we need 2 order parameters. One is composition, which will say which is A rich, which is B rich, and when you have this B rich phase, then the B rich phase should be identified using eta 1 and eta 2, okay. So, at least we would need 3 order parameters in such a scenario. So, if we reduce it to 2 order parameters, for example, so I can think of a situation where alpha and I have beta, okay. Alpha and beta differ in composition, and let us say they also differ in their crystal structure. So, then I need C and some phi to refer to the crystal structure and C to refer to the alpha or beta phase, okay. So, there are some scenarios like this where we want more than one order parameter, and it so happens that one of them is conserved and the other one is non-conserved. In other words, we are going to put together the Allen-Kohn and Korn-Hilliard equations together, and when the microstructure evolves, when the beta phase grows out of this alpha phase or the beta phase shrinks in this alpha phase, then when the transformation happens, both the composition and the crystal structure are going to change. So, both have to be tracked. So, this is one scenario where we need more than one order parameter to be solved simultaneously. The other scenario where one can think of such a case, and this is the case for which it was implemented by us. So, let us look at that scenario. So, there are classical growth theories for precipitate growth. One of them is due to Zener and Frank. They independently came up with this growth theory. That is, suppose if you have a matrix and if you have an isolated precipitate growing out of the matrix. So, I have alpha, I have beta. So, if I look across the composition profile, so as a function of position, the composition will look something like this. So, I have a supersaturated matrix. So, alpha is supersaturated. By that what we mean is that it has more B than what equilibrium alpha would like to have, and you have this beta precipitate that is growing, and Zener and Frank assumed that you have an isolated precipitate that is growing in a supersaturated alpha matrix, and they came up with the expression for the growth rate of such precipitates in 1D systems, 2D systems and 3D systems. Now, one of the things that Zener and Frank assumed in their theory is that the precipitates are isolated and it is a supersaturated matrix, and the diffusivity D is a constant. Okay. And one of the things that they did miss is that they assumed no Gibbs-Thompson effect. Okay. Now, this assumption of no Gibbs-Thompson effect is okay for the 1D growth kinetics, because like we saw yesterday, in one dimensional case there is no concentration change. The beta precipitate and the alpha precipitate across a planar interface will have the composition that is given by the equilibrium calculation. However, when you have a curved interface, that will happen in 2D and that will happen in 3D. In fact, curvature in 3D will be much higher than the curvature in 2D. In such a scenario, suppose you are assuming that a circular precipitate is growing or a spherical precipitate is growing, in which case curvature will be twice as much in the case of sphere as compared to a circle. In those cases, then we want to know what is the effect of Gibbs-Thompson on the growth rate. Suppose we are interested in knowing this. So, for doing this, again you have to use two order parameters, and one is the composition order parameter, which distinguishes between which is alpha, which is beta, which is A rich and which is B rich phase. So, that is for the two phases, and we also have to introduce this order parameter phi, which is to say that this is the beta phase. So, whatever C is 1 is say beta, and whenever C is 0 is, let us say, alpha or 0.1, 0.2 etcetera, depending on what supersaturation we have. Now, phi will be such that in beta phase it will again take a value of 1, and in alpha phase it will take a value of 0. The reason why we are introducing this phi in this scenario is not to distinguish between the two crystal structures, even if they are same crystal structures. By introducing this extra variable phi, we can make sure that in our phase field model the diffusivity remains a constant. So, that is the reason why we are doing this. Why is this so? We know that diffusivity in the phase field model is given by the expression. So, it is related to the mobility m through the curvature, second derivative of the free energy with respect to composition. This is nothing but d, right. So, this we have derived in one of the earlier lectures. So, if I want to keep d a constant, because in the phase field model we deal with m, and the usual f that we assumed, f was assumed to be a c squared into 1 minus c whole squared. So, dou f by dou c will be 2 a c into 1 minus c into 1 minus 2 c, and del squared f by del c squared, this also we calculated yesterday, will happen to be 2 a 1 minus c into 1 minus 2 c minus 2 a c into 1 minus 2 c minus 4 a c into 1 minus c. As you can see, del squared f by del c squared takes a value of 2 when c is equal to 0 or 1, right. So, that we saw yesterday. For example, if c is 0, then these two will disappear and this will give me 2a, and so del squared f by del c squared at c equal to 0 is 2 times a. And you can also see that if c is equal to 1, for example, this term and this term will disappear. So, you will get 1 minus 2, that is minus 1. So, you will again get C to be equal to 1 to be value like 2a. If I take C equal to 0.5, then these two are going to disappear, and this is 1 minus 0.5. So, that is 0.5, and 0.5 multiplied by 4ac, that is 0.5 is 1 by 2. So, it is going to give me minus 2a. Of course, this is expected because we are looking at free energy which has a double well and a concave region. In that region we expect the diffusivity to be negative. So, for the same m, this is going to give me, if a is assumed to be 1, this is minus 2 here, plus 2 here, plus 2 here, which means from plus 2 it is going to go to minus 2, and from minus 2 it is going to become plus 2. In other words, the diffusivity is a function of composition, and it is actually this function of composition. So, if we want to now compare the analytical solutions of Frank and Zener, okay, so that is first thing we want to do. Let us assume that we are looking at a planar interface growth. So, I can look at the one dimensional growth problem, and I want to see if my phase field model actually gives the same solution as Frank and Zener. Then I need to make sure that I choose a system in which this del squared f by del c squared gives a constant value irrespective of what c is. So, it has to be only a second order function in C. So, but quadratic function in C is something that is going to look like that, right. You are not going to get this kind of barrier. So, you are not going to be able to grow a precipitate in a supersaturated matrix, because the two phase coexistence means that your free energy should have this kind of concave curvature. So, that is the time when you will say that, okay, so there is equilibrium and this is alpha, this is beta. So, one of the ways in which you can achieve by having this kind of free energy curve is by taking two such free energy curves and connecting them through the second order parameter, that is the phi order parameter. So, I am going to show you exactly how this is done, but this is one of the reasons why you might want to use more than one order parameter. Okay. So, in this scenario, then we will make sure that we choose the f appropriately so that the diffusivity remains constant. So, we have a system in which the diffusivity is constant. So, we can compare the results with Zener and Frank in one dimension, because there is no Gibbs-Thompson effect in their model, and it is true in our numerical simulation also. We should be able to match the solutions, and if they match in 2D, where there is Gibbs-Thompson effect in the numerical implementation and when there is no Gibbs-Thompson effect in their analytical calculation, one can then compare and see the difference in terms of Gibbs-Thompson, and one can see why or how much is the contribution of Gibbs-Thompson effect to the growth rate. So, this is possible to study. Now, we will look at the Zener-Frank model itself, how they came up with the analytical solution as a tutorial. So, it is a very nice paper which with some functions that you can evaluate easily using a GNU scientific library or using Octave, you will be able to get the solution or at least the growth rates for different supersaturations that Zener and Frank came up with. And then one can go and do the numerical simulation and compare with them. In the case of 1D we should match, and in the case of 2D we should be able to separate out the effect of Gibbs-Thompson to the growth rate. Okay. So, if you want to do such a model, again you need this kind of two order parameter models. One conserved order parameter composition, because that is the problem that we are looking at, it is a precipitate growth. The other non-conserved order parameter is chosen for some numerical reasons. This is one of the reasons why we do simulations. Simulations are done so that in cases where you are not able to relax certain assumptions or approximations in real life, you can try to do them in the simulation and then try to separate out the effect of any particular phenomena on what you are studying. So, this is one of the reasons why we want to do. So, in that context, it becomes important to write a phase field model in which we have two order parameters, one conserved and one non-conserved order parameter. So, let us try to look at what such a model looks like. Of course, as usual, so I am going to describe a model which is something like this. So, what does the model look like? The model looks like this. So, I have a matrix, I have a precipitate, and I call this as alpha, this as beta, and I decide to describe this microstructure using C and phi. These are the 2 order parameters that I use. Okay. Of course, the first thing we have to do is to be able to write the free energy, and once we write the free energy, then we have to write the Cahn-Hilliard and Allen-Cahn equations. Okay. So, writing this free energy is the crucial thing. So, how do you come up with the right type of free energy? It has to give constant diffusivity, which means the C terms that we introduce in the free energy should not be more than quadratic. So, there should be only power 2. So, that is one of the constraints that we have, and as I indicated, there are many different reasons why you do this, and in this case we are doing this just for this problem of making diffusivity a constant. In the standard Cahn-Hilliard, diffusivity is not a constant. So, we are building a model in which the diffusivity will be a constant. Okay. So, the free energy expression, okay, by NV is something like that: f of C comma phi, 2 order parameters, plus kappa C del C squared plus kappa phi del phi squared. Of course, there are no surprises here. If you have 2 order parameters, their gradients also should be part of the free energy functional we have written. The most crucial thing is the choice of this f of C comma phi, because this is the term that is going to couple the C equation and phi equation. Remember, our Euler-Lagrange equation is going to be dou f by dou C minus del f dou this f by NV by dou del C, right, or in the case of phi, that is going to be dou f by dou phi minus del f dou of f by NV by dou del phi. Okay. So, this term is going to give you the square term, I mean del squared phi or del squared C term, and this dou f by dou phi by dou f by dou C, this then, because f is a function of C and phi, is going to be a function of both C and phi. This is also going to be both a function of phi and C. So, that is why these 2 equations are going to be coupled. So, these are coupled nonlinear partial differential equations which have to be solved simultaneously. So, the choosing f of C comma phi happens to be the most crucial thing. So, this was done by one of my colleagues. So we have studied such a system. This is a paper that was published in Acta Materialia some time back, done by Professor Rajdeep Mukherjee. So, what he has chosen, what we have chosen as the free energy is a free energy f of C of phi, C comma phi, which looks something like this. So, the function is of course a C squared into 1 minus w w of phi plus b 1 minus C whole squared w of phi plus p times phi squared into 1 minus phi whole squared. Okay. So, of course, there is a double well potential for the phi itself, which is expected, and it has a minima at 0 and 1, which is what we wanted, and so also is C and 1 minus C, because AC squared will have a minima at 0, 1 minus C whole squared will have a minima at 1, and this phi will align with those 0 and 1, and so we are going to get this. The most important thing is this W of phi. It is called W of phi because this kind of function was introduced by Wang et al. In one of their models. So, it was a model which is to study solidification, where again you have the temperature and the phase field, the solid or liquid. So, there are 2 order parameters, and the coupling is done using similar functions. So, what is this W of phi? So, it is a function which is defined like this, is 0 if phi is less than 0, is phi cube into 10 minus 15 phi plus 6 phi squared if phi is in the range 0 to 1, is 1 if phi is greater than 0. Okay. Now, why is this function? So, it is a fifth order polynomial, and it is a fifth order polynomial because this function is defined in such a way that it goes to, so let us take so this is 0 and this is negative. So, it goes to 0 when this function is 0 obviously, and it remains at 0 when you are below 0. It goes to 1 when this phi is 1. Okay. So, 10 plus 6, 16 minus 15, that is 1, and 1 cube is 1, and it remains at 1 if it becomes greater than 1, right. So, it is going to go there. In between it is going to change, and the function is written in such a way that, of course, obviously if it is going to, so there are conditions like it has to go to 1, it has to go to 0, there are two conditions, and it has to remain 1 and remain at 0, but it has to reach this 0 and 1 in a smooth manner. In other words, the slope at 1 and 0 at these 2 points should also be the same, and there is a inflection point somewhere here. So, the curvature changes. So, there are 5 conditions. So, the simplest polynomial that you can write which will obey all this happens to be this function. So, let us first do that. Let us try to plot this function in Octave and see how this function looks like. So, that will be the first exercise we want to do using the computer. So, let me call this as Wong et al. Function dot oct. Okay. So, I am going to define this function. So, how do I define this function? So, there are several ways in which we can do. So, I am going to do the simplest way. So, I am going to say a function y is equal to f of phi, right. So, that is how the function is defined. What is y? Y is equal to phi cube so into 10 minus 15 phi plus 6 phi squared. So, that is y end function, right, the phi function. So, I am going to say for I equal to 1 to 141, if phi of I, okay. So, let me first say if phi, so let me do it differently. So, let me say if I is equal to if I is equal to 1, then let me say phi of I is equal to minus 0.2. Okay. So, else phi of I is nothing but phi of I plus 0.01. Okay. So, if you do it 141 times, if you keep adding 0.01, you will reach 1.2. Okay. So, this is end if. So, we have now defined the phi to go from minus 0.2 to 1.2, and now we want to calculate. For doing that, if phi of I is less than 0, then we say that this function w of I to be equal to 0, right. Else if phi of I is greater than 1, then we define this w of I to be equal to 1.0. else we define W of I to be f of phi of I and if and for. So, we have now run from minus 0.2 to 1.2 and we have calculated W and it is consistent with our definition. So, let us plot phi comma W. Okay. So, this is the function, let us see. Okay. So, there is a problem. Okay, line 7. Sorry, this is should be phi of I minus 1 plus 0.01. Right. So, you get this function, as you can see it goes to 0, and if we concentrate here, let me get this function. So, if I concentrate in this region, you can see that it goes to 0 and remains at 0, and the way it goes to 0 is very smooth. And similarly, if it goes to 1, it goes to 1 and it remains at 1, and the way it goes to 1 is also very smooth. And in between, as you can see, because it goes like this and then it goes like that. So, there is a change in the curvature that would happen somewhere here. Okay. So, this is the Wong function. So, that is the function that we are using in this expression. So, if you look at this f of c comma phi, we have this two wells which will make the minima at c equal to 0 and c equal to 1, and this part of the function will make sure that phi also has minima at 0 and 1. So, C0 phi 0 will be one minima, C1 phi 1 will be another minimum, and in between these minima it is going to interpolate using this W of phi and 1 minus W of phi, that is this function. So, these minima are connected through this type of function. So, what does this function itself look like? Okay. So, that is what we want to do next and plot and see. So, for doing that, okay, so let us write an octave script which does this. Let us call that as Vi f f of c and phi dot OCT. Okay. So, let us call that. So, that is the function. So, I now need to define the range. So, let me first define the C as Lin space minus 1.2 to 0.012 sorry 0.2 minus 0.2 to 1.2 in some 141. So, that is the C. Let me also define phi to be Lin space and that again goes from 0.2 to 1.2 in 141. Okay. So, I want to now, because the f of c comma phi is going to be a surface, there are two variables c and phi and then the function value. So, it is going to be a surface. So, to plot that we need the mesh grid. So, I am going to define c comma phi as the mesh grid of c comma phi. Okay. Now, we need to define the f which should be a function of c and phi, and for doing that, so I also need to define a equal to 1, b equal to 1, p equal to 1, and first we need to define w. So, let me define the w function. So, w will be a function of this phi. Phi is a mesh grid So, we also need to define, okay, so let's generalize a little bit. Let me say n equal to 141 and lin space will be with n points and this lin space will be with n points. Okay. And so, the mesh grid phi is going to be an n by n matrix. So, what I am going to do is that I am going to define these functions. Okay. So, y is equal to function y is equal to f of phi, let me call it as w of phi end function. And how is w calculated? W, so y is equal to phi dot star phi dot star phi dot star 10 dot minus 15 dot star phi plus dot plus 16 6 dot star phi dot star phi. Okay, so this is the w that is returned, and so if I take, so first let me calculate w for this capital phi. Okay. So, I am going to define Wang function is equal to w of phi. Now, this function, because now we have not put the conditions on what happens to it if it is below 0 and above 1 and all that. So, now I have to run a loop for I equal to 1 to n star n, because this phi is a mesh grid. Okay. So, it is an n by n mesh. So, the Wang function is calculated for each one of those phi. So, what I am going to do and for, so now I am going to say Wang function I. So, if Wang function I is less than 0, Wang function I is equal to 0, else if Wang function I is greater than 1. So, Wang function I is equal to 1. Okay. So, end if. So, I do not need this, if, else, if. Okay. So, now this Wang function will go from only from 0 to 1 as required, and hence we can define our function f as equal to a dot star c dot star c dot star 1 minus Wang function 1 dot minus Wang function plus b dot star 1 dot minus c, so dot star 1 dot minus c dot star Wang function plus p dot star phi dot star phi dot star 1 dot minus phi dot star 1 dot minus phi. So, this is the f function we have calculated. So, you can now say mesh which is c comma phi comma f. Okay. So, that will be the function that will be plotted. Okay. So, there is a problem here, syntax error. Okay. Else if is needed because I still have a condition here. Okay. So, now you can see the function. So, this is the double well potential. As you can see, it has one minima here at 0 0, it has another minima at 1 1, and in between it is straddled by this Wang function. Okay. And that is how this well looks like. So, now probably you can see the well here and the well here. So, in between there is a maximum and in between there is a maximum, and here at these two endpoints it has a higher value. Okay. So, this is how the Wang function looks like, Wang function incorporated with the C, the composition, and the next step is, of course, we have written the free energy, we have to write the evolution equation based on this free energy and solve it using the computer, which is what we will do in the next part of this lecture. Thank you.